right. Can everyone see that?
We can see your slide. It is occupying the entire screen.
All right. So I'm Brad Nelson, and I'm going to talk about an issue or sort of an area that has come up a little bit in various forums of late. Don Golding's poked at it a little bit like last Fourth Day, and I thought I'd do a little bit of an exploration. So one of the things that I think is a key superpower that Forth has is the ability to build domain-specific languages. It's a thing that Forth does, I think, really better than basically anybody else. And uh, basically, what you can do is use Forth to build mini languages to fit the problem that you're trying to solve. And this is sort of not some obscure thing. It's actually pretty widely used in the Forth community to good effect. Certainly the most common is probably to build an assembler for a target architecture. I've used it myself and seen it used to do graphics where you specify sort of a stack of transformations and do things. I've used it myself also for 3D modeling to build shapes to print on a 3D printer. You can build user interfaces this way. Forth is one of the few languages where it doesn't come out of the box with the ability to do structures and object-oriented programming, but you can build them yourself with the pieces that you have and build a sort of domain-specific language for structures. And Polyforth, for example, built up a domain-specific language around database access. So it's definitely a widely used thing. For example, I always got to flash up whenever DSLs come up, assemblers. I always feel like I got to splash up Bill Ragsdale's awesome six block 6502 assembler. And it's not only can DSLs be something that you can use in Forth, but they're not hard to create. They're not big. They're often simple and beautiful. And but a thing that this, of course, I got to thinking the other day is that, well, Infix math is itself a kind of domain-specific language for algebraic expressions, but Forth is typically does RPN, and yet we sort of boast that Forth can do all sorts of relevant DSLs. Why not Infix? And so this talk is my attempt to explore that question a little bit, noodle on the concept, look at a few approaches to how one could do it, and kind of wonder about some things like whether it's a good idea, whether it's a useful thing to that we sort of dodge, or is, and what would the limitations of it be. So there's a bunch of prior art in this space. It's certainly not the first person to look at Forth and say, oh, well, could we somehow make it do Infix? In this talk, I'll reference some work by Brad Rodriguez, who looked at doing parsing in Forth, and Bob sent me a reference to some work he's done in Cozy around parsing. The one that actually always jumps to mind for me is in Julian Noble's book. He actually goes into some of the innards of his formula translator that he implemented, where he after going through describing in the book Scientific Forth ways to manipulate numerical things in Forth, he then sort of concedes that, well, but a lot of times in scientific domains you are dealing with expressions that come from math, and that it's inconvenient to try to translate these always to RPN. And so he builds a tool he calls a formula translator that is able to handle infix expressions. Amusingly, I went looking and seeing, could I find a reference to the to sort of the full implementation. And my copy of the book, which I had for back in the day, I noticed printed at the front of it that I got a copy without the diskette. But fortunately, nothing disappears on the internet, it seems, and I found somebody who has a copy up on GitHub of the diskette. In fact, he's even got I believe the contents of the entire book. So let's talk a moment about forthy style domain specific languages. They typically are kind of an interesting mix. In some most other languages, when you build a DSL, you will often kind of go. It's really about building almost a whole programming language. You'll go out and you'll use a parser generator, and you'll kind of go the full length of saying, I'm going to build this external tool and then incorporate it into my language by way of the build system. And so, a typical example would be Lex and Yak in the Unix world, where you'll kind of build a whole separate external tool to do a thing. Whereas in Forth, what we tend to do is we balance how useful the DSL is against the ease of implementation. We don't necessarily make it something that has error checking, where if you get if you're using a Forth assembler and you put the wrong things in the wrong order on the stack, then it's just not going to do the right thing. And that's a nice trade-off, I think, in some ways, because it lets you use provide the parts that are useful without getting stuck with the complexity of getting it 100% perfect at all the edge cases, which oftentimes you can have more error checking that's needed to sort of handle a domain than there is to handle the success case. And then the other thing is that Forth DSLs tend to use an RPN-like syntax. So you'll get things like, red LED on or left motor off. And when there is parsing, it tends to be typical parsing for Forth. You'll look ahead maybe to get the name of something off of the parse stream, but you don't typically do things that are involve sort of actual full-on parsing. You tend to just do Forth as usual, word at a time execution. And you'll oftentimes get composition naturally. And what I mean by composition is, if you have a DSL for, say, doing something like graphics, or you have an assembler, you'll oftentimes want to intermix this with something else that isn't you're not just sort of doing assembler the way you would in a standalone assembler. You're mixing it with perhaps calculating some set of addresses that you've done in the rest of your code base. Or if you're doing graphics, you maybe want to provide the source of the particular thing you're going to draw partially from something else. And so you can usually get it to be something where you can combine your DSL with the rest of Forth, or with some other DSL in Forth, but you'll tend to have to kind of know a little bit about the implementation, or rely on what I would call kernel knowledge of sort of what's going on behind the scenes. So it's a place where the abstraction of the DSL sort of falls apart. So anyways, I'm going to dive in, and I made an attempt at for my first attempt with doing Infix math. I thought, well, let's try to do sort of the minimum thing that will compose with the rest of the language, but is something that I can kind of fit in a screenful. And the approach that I took for this first attempt is I said, well, let's just support the idea of taking an expression and then some operation, and then look ahead one word. And what I mean by this is that what I really want to make work is 1 + 1 = 2. If you happen to have something more complex, then I'm not going to worry about things like order of operations. I'm going to assume left to right order. And then the other thing is that I think gets mixed in sometimes when folks talk about Infix and Forth is there, very quickly, a problem. So the stack in Forth solves two problems. It solves the problem of the complexity of parsing Infix, but it also solves the problem of needing to have local variables. And so there are Forth implementations of local variables. Micro eForth has one built in. gforth has one built in. Both use the curly braces to declare a set of local variables. But when you're using the stack, you can use just dupe swap over and so on to live without it. And so I think folks conflate the desire for the one with the other sometimes. So in all of my explorations here, I'm assuming that you've got local variables and that you want to be able to use them intermixed with your Infix syntax. So this is the implementation that I initially came up with, and I first wrote it in a way that is relatively agnostic to. So both of these that I'm going to show for this first one are we're done with Micro eForth. Micro eForth it probably doesn't comply to any of the various ANSI standards completely, but it is some weird overlap of the facets that I found compelling. But I've tried to stick to fairly vanilla things. So the idea here is just that I've got a word that lets me find the address of the input stream, and then I check to see whether I'm at the end of the input stream with this full word. And then I override paren because I want to make paren do something interesting. I want it to go and basically scan ahead until I find a balanced parenthesis on the opposite side. So as I go through, I keep a count on the stack of how many layers nested I am with parentheses. And then I'm counting up or down until I get to the point that the value on top of the stack is less than 0. And so what that will do is grab out a big chunk of text that goes from one parenthesis to the corresponding parenthesis. And then once I have that, I have a little bit of a problem because I don't necessarily want to execute that directly because I might want to have more look ahead. So I set this pending flag, and then I go ahead and I try to evaluate that expression, and so that lets me sort of evaluate one subrange, and then I use this. So that's what parenthesis does, and then let's look at these around every operation that I want to make work with Infix. What I'll do is I'll do a scarf, what I call a scarf step, and then an enact step. And so the scarf step is basically, it tries to read ahead one blank space, so one, to the next symbol, and evaluate it. And then if there was anything pending, like if I had if for example I did 3 plus open paren, then I want to go ahead and evaluate that chunk of text as if it's a paren. And the reason this is a little tedious, and it'll maybe make some more sense when I show the next version that uses some kernel knowledge of micro eforth. But basically the idea is that if you've got 3 plus open paren, you need to not only execute that one string paren, you need to look ahead all the way to the next paren. And then after you've done whatever the thing on the right-hand side is, then you've got both the left-hand side and the right-hand side sitting on the stack. So then you can go ahead and then execute execute and or compile the operation that's here. And so this lets you have a plus, minus, times, but it doesn't do anything with order of operations. I'm able to simplify this slightly in micro eforth because there is a word that is actually used in the core of the system to evaluate only one word forward in the input stream. And that lets me get rid of all this business with the pending variable. And what goes on there is that instead, when I do this scarf operation where I want to look one symbol ahead, all I have to do is say, well, I want to execute the next word and any of the ramifications of that word and the things that it goes on to parse, and then return back to where I'm at. And that's really what I want. When I do 3 plus open paren, some expression, and then close paren, I want to get all the way to the end of that. And then I can go ahead and enact the operation, either compiling or executing it. And also I'll call out that all of these words need to be immediate so that they'll work, so that I can have them do the right thing, either compile time or execute time. And so this actually works reasonably well. If your expectation isn't that you're going to get proper order of operations, you can do things like 2 plus 3 plus 4 and get a valid result. You can, if you do things like 2 plus open paren, 3 times 4, close paren, you'll also get the right answer. And you can mix it with local variables. So if you take curly brace around x to get a local variable for x, you can implement a square operation this way. And then when you want to compose things to where you need to have invocation of another word, you have to be a little bit careful because all of these operations, the plus, the times, they're only looking one word ahead. So they're going to parse the word in front of them and execute or compile that word. And so if you had something like, x at sign, if it was a variable, you'd need to wrap that in parentheses so that you know that you're going to need to do sort of both steps. And the same thing happens like if I want to call this square operation, I have to wrap it in parentheses and then go ahead and do the plus. And so I can do a Pythagorean triple here and get the 25. It's notable that, if you do something like 2 plus 3 times 4, this is not honoring order of operations. So it will do the 2 plus 3 first, and then it will do the times 4, which is not what you would expect in conventional notation, but is easier to implement in one screenful. And this is a little bit like there's a calculator that actually is still apparently used for one of the accounting exams, the HP 12C. And when they made a sort of a refreshed edition around the millennium, they thought, well, let's graft, folks have trouble with RPN. Let's graft in a mode where it will support parentheses and in Infix. And on this particular calculator, they chose to not implement order of operations, of course, because that is a can of worms. And so they instead do things in the order you put them in, kind of like a simple 4-function calculator. And so common pattern to sort of ignore order of operations. And so maybe an okay path there. But I thought, well, okay, that's kind of the minimalist approach, the least you could do. We'll talk in a sec about whether any of this is a great idea, but what if you wanted an actual grammar? What if I wanted order of operations to work correctly? And of course, the problem would be, I only bothered to implement plus, minus, times, and divide. But the minute you start, doing a proper grammar, you're gonna wonder, well, what all do I add? What if I want to add a factorial operation? What if I want to add some a modulus operation? That's Infix as well. And so you'll want some way to make it expandable, sort of not only when you first add the set of operations, but maybe as you're doing more with it. And again, I'll continue to reuse local variables. So again, to call out, like, I think that the problem of whether or not you want to try to have Infix in Forth is separate from the question of whether you want local variables. So I'm going to use a technique that is a sort of an evolution of an approach that Brad Rodriguez used a bit back. He has a paper. I think I throw up some of his code in the screen in a moment. But there is a notation that is typically used for expressing grammars, Bacchus noriform. Due to Bacchus is one of the original Fortran folks. And it's a way of describing a context-free grammar, which is just a set of rules that maps non-terminal symbol, which is things like a term or an expression, into a mix of other symbols. And so if you go through a series of transformations on your expression, you'll eventually have described all of the possible things that you could parse. And so, for example, you could you'll use a pipe symbol for conjunction. So you could a full name might consist of a first name, a middle name, and a last name, or an expression might consist of a term, or an expression, an operator, and then another term. And so, in that way, you can kind of build up your grammar by describing each of the constituent components of it. Similarly, like an integer maybe consists of either a digit or an integer followed by another digit. And so it's the sort of maybe not the most general way to parse, but a relatively general way to parse. To handle it in its full glory, you end up needing to do backtracking, which is one of the reasons that people will, in other domains, will typically use more constrained versions of this grammar. Brad Rodriguez has this great paper on BNF parsing, and he comes up with this this BNF parser that is, I believe it's, let's see, I believe it fits actually into basically one screenful. So this, and I'm not going to go into the innards of it. It's quite a bit of intricate manipulation on the stack. But basically, what he ends up doing is allows you to define a symbol like this character here. And, well, actually, sorry. So he starts with a defining word token that lets you associate a particular ASCII character with a symbol that will parse that one character. And then you're able to build up, for example, here he's got parenthesized expressions where he's describing this parenthesized S. This is like a Lisp S expression. So an S expression can consist of either parentheses, another S expression, and a closed parenthesis, and then another S expression, or it's a character and then followed by another S expression. So he's got a bunch of symbols that he builds up, and this is just a small example. And the key thing that he's doing in this implementation is that he is using evaluation as a way to sort of short circuit and do backtracking. So when you do this BNF colon word, he unsmudges things so that you're able to do recursive references, and then he sets things up so that you'll try kind of the first option before a bar, and then if that fails, you abort back up the return stack. And he's got the reason he has a lot of complicated return stack manipulation is that in that case, you abort and then you go and try the next one. And similarly, you can abort. And this lets you try parsing down this path. Is it this case? If not, you fall back. And a key thing that he does in that process is that he also manipulates DP, which is the address of the dictionary. So if in the process of parsing you had different evaluation or compilation attached to a particular branch and you get down a certain path, he undoes all of the side effects, at least in terms of where the dictionary points to. So it's a little hacky, but it is a clever idea because it makes it very easy to backtrack. So for my implementation, I've made a few refinements. Mainly, I wanted to provide a way to add alternatives later because one challenge with his syntax is that you have to kind of declare all of the alternatives up front as you're defining a given word. So it kind of limits, if you later, for example, decide that you want to have one additional rule for adding a new operator, there isn't really a way to do it other than back up when it was first defined. And then the other thing is that this process that he goes through of evaluating down a path and then aborting and going back is almost identical to what you do inside of an implementation of throw catch to preserve stacks. So basically what I tried to do instead was to use throw catch to accomplish this goal. And then I also tack on things like the interpreter state. And then the other thing is that because what I'm trying to do is to mix this in with general purpose forth, whenever possible, because of throw catch, I can use regular parsing words in forth, things like create and so on, to do things. And then if I want to kind of have an undo when the throw happens, that will happen naturally because it will both bubble up the stack and then it will also undo the parsing. And then I have some shortcuts for string matching and tokens. So here's I'll show you first the format that it handles. Basically, what you do is you have a defining word kind that declares just some kind of thing. And then you use double curly braces to specify a list of terminal or non-terminal symbols, or you can intermix other fourth words because you're really just executing this word. And then if at any point something doesn't parse, it aborts and tries the next alternative. And you can just list a series of alternatives separately. And when you're initially defining a word, you can just list them one by one. But there's also this colon curly word that lets you take the execution token of a kind and then go back and add additional rules. So you can shuffle the order kind of whatever's natural, and also do things like add operators after the fact. So the target language that I've used for an example is this one that starts to look a little bit like a sort of a Pascal or a C-like language, where you can define a word, have parameters to it. You have curly braces to separate out the body of the word, things like this, and where critically the order of operations is actually honored. So the implementation here is actually not too bad. It's actually just two screens for the main guts of it. This kind word is a little contorted. It's basically going, and this is really is just saving the state variable, saving the position of the dictionary, saving the parse, the input stream position, and then it tries to execute a word and will abort and go up the stack and try the next alternative in the case where something goes wrong. Or sorry, this is the case where something goes right, and then it backs up. And in the case where something goes wrong, it goes on to the next word in the chain, restores all of the things about the state, and then you keep going through all the alternatives until if you get to the end and none of the alternatives work, then you just throw. And then that allows you to then treat each of these curly words as just a regular definition, where at the end of the definition, when you close out with a semicolon, you also attach it to a linked list attached to this kind defined word. And so you can add additional ones later. It does execute them in reverse order of definition. So whenever you add a new rule for a given kind, that'll be the first rule that will be tried. And then there's some bookkeeping words around being able to look at the parse stream and look at the current token, advance the current token, check if a token matches a particular value, and then I build on that to build an immediate word for having a single character token or a string token. And then, okay, so what grammar to use? I actually literally cribbed a grammar that's from Pascal, because Pascal is kind of known for having a fairly simple grammar. And then I also added the embellishment that whenever you have angle brackets, or sorry, square brackets, you define them, you execute forth in that word. So here's the grammar. I needed to detect all kinds of characters as spaces. I define a kind for multiple white space characters where you either are done or you can gobble up one character and advance forward. I use that to define a white space surrounded token that's one character or is a string. I then define a digit, which is a token in a certain range, and it has the side effect that it leaves the digit value on the stack. I have a word that checks to see if something is a letter or number or underscore, and I use that as the definition of what it means to be an identifier, to have an identifier parsing word. And then from that, I build up things like finding a whole number. I build up evaluation, as I mentioned, of forth inside of brackets. Here's where we get to the actual expression tree. So I've got, I predefine this expression tick because I'm going to need to reference it later in a forward definition. I then, I then define a set of factor. A factor consists of an identifier followed by where you evaluate it, followed by another identifier, or a number, or a parenthesized expression. You can have forth expressions in hard brackets. You can have terms, and then the terms consist of multiplies, divides, mods, ands, and so those, because they're all grouped together in the definition of a term, they have a higher precedence. And then a simple expression with a slightly lower precedence has plus and minus and or, and so you can take sort of almost a direct translation of the grammar you would see in a BNF grammar for Pascal, and I've even got the comparison operations. And in each case, what they're doing is they're actually postponing their evaluation so that it's actually compiling the code that would be associated with each of these. And then that tick expression, I use the colon syntax to close the loop, because when you have an expression in a parenthesis, it sort of goes all the way back down to the bottom of the BNF grammar. And then I just defined initially a statement as just a series of expressions. And so from that, I can have this definition word that says, here is a token. I do a colon definition followed by an open curly brace, and then I go ahead and evaluate the. Actually, why is there this postpone? Anyways, I then can go ahead and evaluate a bunch of statements. Or similarly, I can do this I have this on word that lets me expand the grammar, and I'll give a demo of that in just a second. And then this expr word, what it does is it compiles an expression and then executes it. So it's an opportunity to run something interactively. And so this lets you do things like this on word lets you expand the grammar. So if I decided that I wish I had an XOR operation that wasn't in the grammar, I can say, well, when you have a term, actually the term can consist of a factor, I'll use a caret token for XOR, followed by another term, and then the way that you implement it is by postponing an XOR, and then you are immediately able to use it in this expression evaluation. So I'm gonna actually I'll pop out for a demo in a second, but actually, now's a good moment to do that. So let me quickly show folks both of these things, and I will. Oops, and let me go. So I'll show off the infix, the small infix thing first, and so. I've put it in its own vocabulary, and so now if I have something like 3 plus 4 plus 5, that will just go on the stack. If I define a word where I say something like times 2, if I go look at what it compiled, it actually compiled it 2 times. Things like that. If I define a word like square, and so this is that simpler definition version of things. And you'll see local variable references inside here. And then let's take a look at this this other variant of things. So here I can evaluate expressions like 1 plus 2 times 3, and it will give me the correct order of operations version of things. I can define a word like foo that takes A and B, and maybe I do 3 times, and actually, so one nice thing about the BNF parser is that spaces matter less, and so I can do things like this. And now if I look at if I take let's say 10 and 100 foo, it will have multiplied the first one by 4. The first one by 30 and the second one by 40, or by 100 and the second one by 30. And the word inside is just compiled as is. All right, I'm going to switch back to the other thing really quickly, and a couple closing remarks. So let's see, double check that's the one. Okay, so overall, an unconstrained BNF parser is potentially kind of slow because this isn't the technique that most languages use to parse, because you can end up backtracking, and if you have a very complicated grammar, you can end up sort of exploring a pretty wide tree. And one of the risks whenever you have a BNF grammar is it can be sort of unbounded. You might end up with a grammar that sort of takes infinite time to parse. The other problem with the second approach is that when you have an error case, it throws and then it tries to kind of unwind the state of things, but it doesn't really give a lot of useful feedback. And if there are any side effects that were not captured by the state of the dictionary, the state variable, and the parse stream, you can leave things in a really bad state. And then it doesn't work as well interactively because of refill. That's probably a fixable issue. But basically, it's making the assumption that as it goes forward and backward when parsing or unwinding, that it has the entire input stream. So it works fine for a single line or for an input file, but it doesn't work if you break up the expression in multiple lines. But all of that is probably fixable with some effort. If execution efficiency, I'll mention there is a technique called left elimination, which is what's typically done when people build parsers that they want to have be efficient. And if your grammar has the right structure, you can sort of decompose your grammar into more rules where you put the non-recursive symbols first, and that will simplify the act of exploring the parse tree. This can basically doubles the size of your grammar, can make it a little bit harder to follow. It may also clash a little bit with making it easy to sort of graft new things into the grammar, but that's one possible way to fix it. But the real question is this forthy and is it good? I mean, it's nice in the sense that you can add new words and you can add new grammar, and so you can have your infix. You could add fairly arbitrary grammar. You could even do things like syntaxes that maybe try to look like English. The root implementation is fairly simple, as you saw, sort of 2 screens full. Most of the complexity ends up being in the grammar. The backtracking is weird, though, and I think that it's hard to kind of even visualize when it goes wrong, what's going wrong, because you're going down an expression. If something throws, now maybe you're down some other part of the grammar. And if you do the reduction to left recursion, I think that'll just be messy. The other thing is that you'll notice that I use postpone inside of there. I did a bunch of stack operations inside the individual terms, and I think it demonstrates that sort of it's still forth sitting underneath, and you still have to think about the stack. And so I don't know that it necessarily is its own special abstraction. It's just forth doing a DSL for Infix. So a lot of problems with that one. The first one I think is at least simple. I think the reason people bring this topic up is this one. Would it help with adoption? Certainly Infix, people expect Infix. Infix is, we spend, years and years of people's primary and secondary school education having them work with Infix notation. So it's pretty sticky stuff. But I'm not sure, because I also worry that if you have something that's Infix, people start to expect that it will be Infix everywhere, that's the bottommost abstraction. And that simple initial implementation I showed, a challenge there is that that one's particularly surprising. It doesn't even do order of operations. It expects that you have spaces between each of the symbols, and I think that if it failed to work at some point, it could cause more confusion than it would save. And the more things start to look like other languages, the more people just expect that that's what it is, and then are we really doing forth? So I don't know. Love your thoughts, feedback, questions, or comments.
Well, of course, I definitely have comments, having come from a world of Infix, APL, and K, and also essentially your first version is pretty much what my approach was in that script on essentially just have a word that goes and looks forward and executes the next word, and whatever, and that word, you don't have to go any further than going and saying, okay, execute the next word. If that word goes and just returns a result on the stack, then you have your right argument. That word itself can go and say, okay, go and look further, further to the right and so forth. And again, the implementation of that is pretty simple. I never finished it because I mean I did that quite early on when I was coming from the APL world, but then I got more comfortable with RPN. And one thing I'd never throw away is white space as being the ultimate delimiter. That simplifies it allows you as a human to know the same parsing that the computer does. And you look at some APL has become so complex, as I pointed out in one thing. And anyway, when I go and show stuff, you'll see some of these advantages. But the big advantage of Infix is that the verb, the function, delimits its two arguments, and this most generic, the two most generic forms of functions, combinators, is I don't know what the hell it is. When you have a single, it's monadic is the term in APL. You have an argument, which in APL is on the right, and forth naturally it's on the left, the top of stack. Or you have two arguments, the Y combinator, and essentially everything can be reduced to one or two arguments, particularly if you have lists. And the syntax in APL that is important. And the other piece that's in that script is having strands, because in APL you have entire strings of numbers. So to be able to have, okay, this list, this vector is my left argument, and this vector is my right argument, is cleans things up, and you'll see I have to throw in paren forms to go and say, okay, this is my list, my numeric list, and so forth. But anyway, that's the real thing. This Y combinator, there's a real reason why math notation for hundreds of years has used infix, because saying 1 plus 2 or A plus B is definitely, it defines the separation between A and B rather than having A, B plus. So it's but your first implementation, that really is down at a more nitty-gritty fourth level what I was heading towards.
Yeah, no, and I think it is interesting that even calculators, four-function calculators, often will have the pattern of not worrying about order of operations, and I think people can intuit that, so it is maybe an interesting sweet spot in the space of possibilities, where it's sort of a little bit of an aid, but not so much of an aid that it gets confused with being sort of something else. So, are there other questions?
I'll make a comment if I may.
Sure.
Yeah, so as a longtime Python developer, I expect that the parentheses, I don't have to put spaces in between. And I really resonated with what you said about people really expect infix and have been trained about it for years. That's what's in their minds, much like engineers have vectors in their minds. So infix is really useful because that's what people think, but the space between the parentheses and the argument, I'm not used to it. So anyhow, just my 2 cents.
Yeah, and I don't know if it was clear, but in the second implementation, it is sort of up to the grammar as to how much the space is required. The challenge though is that what ends up happening is if you start doing that, now once you don't have white space as a delimiter, now you have to have rules about, well, what symbols are part of a symbol and what symbols are special and used as delimiters. And so in that grammar, the brackets delimit sort of a pure fourth expression, and then unbracketed expressions, you're not allowed to have a word like a plus or something. Now now that would get confused with an infix symbol. So there's a trade-off of if you're going to have the symbols be part of the symbol and part of, then they can't be a delimiter. So it's a challenge.
Does anybody else remember?
Yeah, two more comments if I can. One is, this is an incredibly important topic, so thank you so much for it. And okay, thank you.
I think one of the big issues is not so much the infix notation as much as operator precedence. I look at all my elementary school years, and it all involves how many inches are in a foot, how many minutes are in an hour. We got to do the multiplication before the addition, and exponentiation. Well, you got to hold on till junior high for that. So in my programming, I got rid of all operator precedence. When I write a program, there are a hell of a lot more parentheses. And then things become very simple. And if I want to convert from infix to something like reverse Polish, it becomes almost trivial. It's just basically where you put your symbol. And so to me, half of the battle is that we've got into this whole thing of operator precedence. And that really gums the whole works up. And so that's my take.
Yeah, it's interesting. There's an analogous situation in the Lisp community where they have prefix notation, but they have a difference with forth, which is that everything in Lisp is fully parenthesized, and so for them, there's this extra kind of nudge of even if you're confused about the way this works, you're at least not thrown by having to visualize the stack in your head. You have the guidance that, well, you've put the parentheses around everything. So I think that is one reason that I've not seen the Lisp community debate, oh, should we do infix? I mean, there are certainly ways you could do it in Lisp as well, but I think it doesn't come up as much because fully parenthesized expressions are that much easier for people to understand. So it's one step closer to something people can follow.
Yeah, and then I wrote my own text editor years ago, which is going to be on a web page, and it was pretty neat because as you put your mouse over a parenthesis, it would highlight the matching parenthesis on the other end. And to me, the real problem is we got stuck with characters that came from a typewriter, a mechanical typewriter. And between color and bold and flashing things and the rest, we have a hell of a lot more tools to match all these stupid parentheses. And if we had a better text editor, I think people would accept parentheses, and I think Lisp would be more popular. And I hate to say it, but because forth is in competition with Lisp in some ways, forth would lose out. That's my take. Sorry.
Just don't add the blink, please. Does anybody else remember the Silicon Composer's C compiler for their fourth engine? Those were the days.
One historical point: the elimination of the hierarchy of operations was a really key thing with Ken Iverson. I mean, that was one of his real sort of core ideas in designing APL. But then he created operators which take also using his later. I like the notion of verbs and so forth. A verb is a function. An operator takes verb, called an adverb, among its parameters, and the operators have precedence over the verbs. But that's the second level that is it's really what makes APL. But eliminating the hierarchy of times and exponentiations, because They're a very small subset of the total number of functions.
It is interesting that, that happens in APL. It's also Smalltalk does it as well, where it's once you start having lots of different operations where it isn't as obvious what the relative precedence order should be. It's actually kind of problematic to have this kind of arcane set of rules of what comes before what. It sort of makes sense for Blackboard algebra, but yeah, it is it's a sort of a closed set that's hard to add to. And so languages like Smalltalk and APL that confront this question of, but what if I have more operators now? What is the precedence? I think tend to end up saying, you know what, let's just have everything be strict order. And
So Brad, are we ready to move on?
sure.
Okay. Any last quick anything for Brad? Okay. Going once, going twice. Sold. Okay, Bob. Bob Armstrong will introduce himself and
Okay, let me share. And let me